Hi, this is Dr. Remenacker. In this particular video, we are going to take on higher order ordinary differential equations with constant coefficients. In this particular video, we're going to limit ourselves to linear um, ordinary differential equations. As we approach solving these, we're going to find that along the way, there are two different algebraic techniques that you've probably learned somewhere earlier that we're going to need. The first of these is synthetic division. And the second of these is row reducing matrices. Sometimes this is called the Gauss-Jordan technique. As a first example, let's consider the equation y triple prime minus 3y double prime minus y prime plus 3y equals 0. In earlier situations where we just had second order linear differential equations with constant coefficients, recall that we would rewrite this as something like r squared. Well, here we would start it here as a minus 3r squared minus r plus 3, and this would really be r to the 0 power. That's why there was just a constant there. As we approach higher order linear differential equations with constant coefficients, we can use that same technique. Essentially what we're doing is we're guessing when we use that technique, we're going to try some form of the solution y equals e to the rx and see what happens. Now, y can be used as e to the rx. Y prime is going to be r times e to the rx. Y double prime works out to be, well, the derivative with respect is going to be r squared e to the rx, and y triple prime is going to be r cubed e to the rx, and I suspect you see the pattern that's developing here. In the earlier situations with second order, where we just substituted r in, this is really what it's based on. And we're going to continue to base our attempts on solving these on this idea of, well, let's try see what will happen if we let y equal to e raised to the r times x. R is a variable that we don't know. That's something we're going to have to find along the way. But notice here, I can rewrite this equation that we have as r cubed e to the rx minus 3 r squared e to the rx minus r e to the rx plus 3, um, and it's going to be just e to the rx. Notice here there is not a coefficient of r in front of it. Okay, so I'm going to box this off, keep this over to the side. This equation that we have here can be rewritten. We can factor out the e to the rx. And what we'll then have is r cubed minus 3r squared minus r plus 3 equals 0. This is where the idea of rewriting second order linear differential equations as r squared r and then a constant actually comes from, just in case you haven't seen this elsewhere. Okay, now we have this situation and we know that one of two things has to be the case. Either this factor or this factor has to equal 0. When you take two numbers and multiply them together, one of them has to be 0 if the product is 0. Well, we first know e to the rx is never 0. We know that's the case, so we know that that particular factor can't equal 0, which leaves us then with the situation of we have r cubed minus 3r squared minus r plus 3 has to equal 0. Okay, so what are we going to do with that? Well, there are third and fourth degree equivalents to the quadratic formula. Okay, if the degree is 2 for the equation, you can use the quadratic formula. There is a cubic formula and there is a fourth degree formula. There aren't any formulas beyond the fourth degree. Hmm. Actually, we really don't want to get involved in that because those formulas, even solving for roots of a third degree polynomial or a fourth degree, those things get pretty nasty. So let's try a different strategy. What we could do is we could start solving for roots. And if you'll recall way back to your times in algebra, okay, if we have a graph of this function, we could sketch out a rough graph of it. And that would go something like this across here, here, and here. And what the graph is going to wind up doing is something like this. So this is kind of a rough sketch of this particular polynomial here, r cubed minus 3r squared minus r plus 3 equals 0. What we're really after are the roots. Okay, we're after this location, and this location. We can start our search by just guessing. For example, if I choose r equals 0, I'm going to wind up with a value of 3, which is positive coming out. If I choose something like r equals a negative 2, the value I'm going to get out is negative. Now, if we go from a negative value somewhere down here to a positive y value, something up there, what that tells us is somewhere between these two values, negative 2 and 0, that particular polynomial has to intersect the x-axis. In other words, there's a root in there somewhere. Okay, so we can go shopping for roots like that, trying to identify locations for them. And knowing this, actually, we could hope that we're going to be lucky and try something like r equals negative 1. And if we substitute that negative 1 in there, we're going to have this negative 1 cubed minus 3 times negative 1 squared minus a negative 1 plus 3. So this is going to give us here a negative 1, and here we're going to have minus 3 plus 1 plus 3, and sure enough, that equals 0. R equals negative 1 is a root for this particular polynomial. So one of our solutions for this polynomial here is going to be r equals 1. Okay, what's that get us? Recall that I mentioned that we're going to need two techniques. In the upper left corner, the first one is synthetic division. If r equals negative 1, that tells us then that r plus 1 is a factor. Okay, so we can take this equation that we have, this polynomial, this r cubed minus 3r squared minus r plus 3, and I'm going to divide that by r plus 1. You may or you may not recall synthetic division. If you don't, hopefully this will bring it back to mind for you. First thing I want to do is I want to determine what value do I need to multiply the lead term in the divisor by to make it look exactly like r cubed. Well, to make it look exactly like r cubed, I'm going to multiply by r squared. And I'll take the r squared times both factors, or times both terms, and this is going to give me r cubed plus r squared. Okay, so we have that. When you subtract this, notice the r cubes subtract. We're left with a negative 4r squared minus r plus 3. Once again, we're going to do the exact same thing that we just did. The question is, what do we multiply r by to make it look exactly like a negative 4r squared? That's going to be a negative 4r. And as I work through this, just a little side point here, notice I'm trying to keep my values, if you would, lined up with the place value. Okay, so I'm going to take this negative 4r and distribute it over r plus 1. So that's going to give a negative 4r squared minus 4r. I'm going to subtract that. So we're going to have a minus 4r squared plus 4r squared. They're gone. We're going to have a minus r minus a minus 4r gives us plus 4r. So we have 3r plus 3. All right, so we now need to identify, what could we multiply r by in our divisor to make it look exactly like 3r? Well, that would be a plus 3. And we're going to then have 3r plus 3. And when that subtracts off, we end up with 0. If you end up with 0, that means there's no remainder, which is good news. This really means that this polynomial that we have here could be written as r plus 1 times, then we're going to have this r squared minus 4r plus 3. Well, the r plus 1's already factored out. And remember, we want this equal to 0, which is what we're trying to solve. Is there some way to factor this second portion? Well, in fact, there is. The second part will factor, and we'll have r plus 1. We'll have an r minus 1 times an r minus 3 equals 0. This gives us now 3 roots. Okay, our roots are going to be r equals a negative 1, a positive 1, and 3. This then allows us to write our solution as the following. Following the same pattern as we did back with second order linear coefficient or constant coefficients, we're going to have y equals c1 e to the root 1 plus c2, that's times x, e to the root 2 times x plus c3 e to the root 3 times x. Using our values for our roots, we can write this as c1 e to the negative 1 times x plus c2 e, the second root's going to be a positive 1 times x plus c3 e, the third root's going to be a 3x, and that is our general solution. That's all the further we can go unless we have some initial values provided, which in this case we don't. General solution to that problem looks like that. Well, what if we were given some initial conditions? Using this exact same problem, suppose that we also knew the following. We knew that y of 0 equals 1, y prime of 0 equals 2, and the second derivative evaluated at 0 equals 3. So in addition to being given our equation, we're given some initial values. From this, we can go ahead and we can then solve for C1, C2, and C3. Let's start with this first piece of information where we have y of 0 equals 1. So we know the y value is going to be 1, trying to keep the general solution in the upper right corner. Okay, using this first piece of information here, I'll just jot this down like this. Y of 0 equals 1 gives us the situation where the y value, the left-hand side, is going to be 1 when we have an x value of 0. Okay, so what's that going to look like? It's going to be c1 e to the negative 0 plus c2 e to the 0 plus c3 e to the 3 times 0. That cleans up pretty nicely. We get 1 is equal to c1 plus c2 plus c3. Okay, so there's one of our equations that we need to solve. Unfortunately, things start getting a little bit trickier. Notice in our second condition that we have here, we don't know about the function itself, but we know about its derivative. Uh-oh, that means we need to first compute the derivative. So y prime is going to wind up being a negative c1 e to the negative x. It's going to be plus c2 e to the x. And then we're going to have plus 3 times c3 e to the 3x. This came from computing the derivative of each of the terms in our original solution. Okay. The first two are pretty straightforward. The third one you have to use the chain rule on. That's where the 3 in front of the C3 comes from. Now that we have that, this allows us to substitute in the information from the first derivative here on our initial value, and it tells us our y value is 2 when x is 0. Now, I go back over to my derivative here, and I'm going to substitute in 0 for the x values. This is going to give me a negative c1 plus c2 plus 3 times c3. There's a second equation. We now need to compute the second derivative. The reason we need to compute the second derivative is because we have a piece of information, an initial value, at the second derivative. Well, that means we're going to have to take the derivative of our first derivative, which is going to give us c1, c1 e to the negative x plus c2 e to the x plus 9 times c3 e to the 3x. As with the previous two equations, I'm now going to substitute in the x value, in this case it's 0, and the y value of 3. So that gives me an equation. 3 is equal to, we're going to have c1, e to the negative 0 is 0, plus c2, e to the 0 is 0, plus, now we're going to have 9 times c3. Okay, so we have 3 equations here, and somehow we need to handle these to get the solution for C1, C2, and C3. There are a couple ways to do this. One is by solving 2 of the equations for C1, for example, and then substitute that into the third one, and then back substitute and find what C2 is equal and substitute that in, and it just gets really ugly. An easier way to do this is by row reducing. What that means is I've got a matrix. Now, if you've not seen matrices before, this is kind of like a spreadsheet where you have columns, and each column you're going to put a particular value. So in the first column, I'm going to put the coefficient from the first equation on C1. Well, that's 1. The coefficient on C2 is 1. And the coefficient on C3 is 1. Now I could put equals, but it starts to get kind of messy. So the standard approach is to use a straight line, equals, and up there on the y value side equals 1. I'm now going to take the second equation, this one, and I'm going to put this in the second row. My C1 has a coefficient of negative 1. My C2 has a coefficient of 1, and my C3 has a coefficient of 3, and the y side is 2. Then I'm going to take the coefficients from C3, or equation 3. The C1 has a coefficient of 1, C2 has a coefficient of 1, C3 has a coefficient of 9, and the y value is 3. Now that I have this, the objective is to add the first equation to the second and third one and zero those out. So what's going to wind up happening here is at the first step, I'm going to leave my top equation alone. But I'm going to add it to the second one. And when I add it to the second one, notice this plus this gives me a 0. And the objective is to get a single number in a column and everything else in that column zeroed out on the left-hand side of the vertical line. To add it to the third one, I need to multiply by a -1, and then I'm going to add it to the third one to get things to cancel out. So I have a -1 plus 1 is 0. I'm going to have a -1 times 1 is a -1, plus 1 is 0. I'm going to have a -1 times 1 is a -1, plus 9 is 8. And in the third one, I'm going to have a -1 times 1 is a -1, plus 3 is 2. Now, I got focused on cleaning up the first column, and what I need to do is finish off adding row 1 to row 2. 1 plus a -1 is 0. 1 plus 1 is a 2. 1 plus a 3 is a 4. And then on the right-hand side, 1 plus 2 is 3. Okay, so I've accomplished in the first step zeroing out one of the columns. So I just have a 1 and everything else is 0. Remember, this first column talks about C1, the second column C2, third one is C3, and on the right-hand side is the Y value. What I now want to do is to, in the second column, second row, this term right here, I want to make that a 1. Well, to get that equal to 1, what I need to do is to multiply that whole row times a half. Okay, so if I multiply that whole row times a half, I'm going to get a 0, a 1, a 2, and then a 3/2. Notice in the third row, there's already a 0 there. Nothing needs to be done with that row except to bring it on down. Okay, so we've got that done. Now, the first row in the second column, we need to zero that out. So what I'm going to do is I'm going to take row 1 minus row 2. Or in other words, I'm going to multiply row 2 times a -1 and add it to row 1. So 0 plus the 1 in the first column will give me 1. Now I'm going to have a -1 times 1 in the second row, which is going to give me a -1 plus this one here is going to be 0. Lastly, I'm going to take the -1 times the 2, which will be a -2. I'm going to add the -2 to this. -2 plus 1 is a -1. Then on the right-hand side, I have my -1 times 3/2. And I'm going to add that to this. So I'm going to have a -3/2 plus 1 is a -1/2. Okay, so we're getting there. What we now need to do is to, in the third row, third column, get that to be a 1. Well, to get that to be a 1, what I need to do is to multiply that whole row by 1/8. Okay, so when I multiply the third row by 1/8, then we get 0, 0, 1, and then 2/8, which is 1/4. The next objective is to zero out the rest of that column. So for example, my new row 3 right here could be added to my row 1 over here. And you'll have a +1 plus a -1, and those cancel out, which is good news. But let's take it column by column. In the first column, I have a 0 in row 3 plus a 1 in row 1. 0 plus 1 is 1. In the second column, row 3, I have 0 plus, in the first row, 0. 0 plus 0 is 0. In the third column, I have a positive 1. I'm going to add it to the negative 1. I'll give 0. Now I have a fourth minus a half, which is a negative 1/4. The next thing I need to do is to get rid of this 2. So I'm going to multiply my new improved row 3 by a negative 2. So in the first column, I'm going to have negative 1, or negative 2 times 0 is 0, plus the 0 in row 2 is 0. I'm going to have 0 because I have the negative 2 times 0, and I'm going to add it to the 1 in the second row. There's 1. Then I'm going to have a negative 2 here, plus the positive 2 that's circled in yellow. That gives 0. Here we're going to have a negative 1/2 plus 3/2, which will give 1. All right, so at this point, this is considered to be row reduced. It's row reduced if you have your 1s along the diagonal, and every value off of the diagonal is 0. This allows us to then read out what our value for C1, C2, and C3 is. C1 is going to be a negative 1/4. C2 is going to be 1, and C3 is going to be a positive 1/4. We can then take these values and we can substitute them into the general solution. And recall our general solution was y equals C1 e to the negative x, and we had plus C2 e to the x plus C3 e to the 3x. But we can read from this is actually called an augmented matrix. The value of C1 is a negative 1/4. So we have a negative 1/4 e to the negative x plus the value of C2 is 1. So we have 1 e to the x. Then we're going to have our value for C3, which is a 1/4. Okay, and that's going to give us 1/4 e to the 3x. This is our particular solution when we solve this problem based on the initial values that we were given up here a ways. Notice these problems don't necessarily come together in 3 or 4 minutes. Okay, this is a situation where you have 3 distinct roots. What happens if you have multiple roots or repeated roots? We'll take a look at that next. Okay, so in our next example, we are going to look at a situation where we don't just have unique roots. Let's consider the following problem. Let's say we have the 4th derivative of y, and remember the notation for that is a little 4 in parentheses, minus 3 times y triple prime, and we have plus 3y prime minus y single prime equals 0. We can create our characteristic equation using the techniques that we've already talked about, you saw in the first one, and this basically works out to be r to the 4th minus 3r cubed plus 3r squared minus r equals 0. Okay, well, one of the first things to notice here is that we can factor out an r, and this is going to be r times r cubed minus 3r squared plus 3r minus 1 equals 0. We could play around with the game of trying to find roots as we discussed earlier. To help move this along, I'm going to just say, hey, look, r equals 1 is a root. We can check that. We have 1 cubed minus 3 times 1 squared plus 3 times 1 minus 1. And sure enough, that does equal 0. So 1 is a root. Okay, so if 1's a root, where does that leave us? Well, that brings us back to our synthetic division. We're going to do r minus 1. Remember, if r equals 1 as a root, that means that r minus 1 equals 0. Oh yeah, there's a factor. So we wind up taking the r minus 1, and we're going to divide this into the r cubed minus the 3r squared plus the 3r subtract 1. I'm not going to worry about the r. I already know that r is one of my roots. So it's time to start dividing. I want to make my lead in my divisor r look exactly like r cubed. So I'll multiply by r squared, which will give me r cubed minus r squared. I'm going to subtract this. The r cubes will cancel. We have a minus 3r squared plus r squared gives us a minus 2r squared plus 3r minus 1. Once again, we want to multiply our lead in our divisor by something, and we want it to look like a negative 2r squared. We'll multiply by a minus 2r. And notice as I put my r squared and my r at the top with the division, I'm lining them up. I'm being careful to line things up. Okay, neatness counts here. So a negative 2r times r is going to be a negative 2r squared. Then a negative 2r times a negative 1 is going to be plus 2r. Going to subtract this. The minus 2r squared plus 2r squared cancels. We have a 3r minus 2r gives me r minus 1. That'll go in one time. So what this does is it helps us to further factor our equation. What we now have is r times r minus 1 times, and we have the rest of this, r squared minus 2r minus 1 plus 1 equals 0. Well, notice this quadratic that we have here still is a factor, will itself factor, and this gives us r times r minus 1. And then this quadratic factors into r minus 1 times r minus 1, and it's equal to 0. Okay, so where do we go from here? Well, we're going to use the same technique as we used for a double root when we were working with a second order linear with constant coefficients. Remember there, our solutions look like e to the rx, x e to the rx, and we're just going to continue that idea on as we go into n dimensions. X squared, then we have x cubed, e to the rx, and right on down the road however far we need to go. So what this does is it allows us to then write our solution, a general solution, as y is equal to c1 e to the r1 times x. Well, I'm going to call my r1 just 1 plus c2 times x e to the r2 times x. So that's just going to be x plus c3 times x squared times e to the r3 times x. Well, the third root is still 1, so that's going to be 1 times x. Plus, now be careful here, we have c4, we have e to the root, which is 0 times x. That root of 0, oh yeah, that comes from over here. When you raise anything to the 0 power, it's just 1, and there is our general solution. Now, if we were given some information, we would need 4 different pieces of information, okay, because we have C1, C2, C3, and C4. But if we had 4 pieces of information regarding initial values, we could create an augmented matrix and go about solving for C1 through C4 just like we did in the previous problem. Let's take a look at something a little different. We've looked at first a problem that had unique roots. Second example looked at a problem with a repeat of the root. Actually, the root repeated 3 times. Let's consider the following situation. If we have something like the fourth derivative of y minus 4 times the third derivative of y plus 8 times the second derivative of y plus 4, oops, got to copy down the right problems here, minus 8 times the first derivative of y plus 4y equals 0. Okay, here we have a fourth derivative. We're going to go ahead and create the characteristic equation just like we typically do. This is going to become r to the fourth minus 4r cubed plus 8r squared minus 8r plus, this could be 4 times r to the 0, which is just 4, equals 0. Oh yeah, that looks like fun. Where's that going to leave us? Well, I'm going to kind of fast forward you to a solution to this. This thing actually factors into r squared minus 2r plus 2 squared equals 0. And if you try squaring that out, you'll find that that really is the solution. Okay, so what are we going to do with that? Well, we can rewrite this, get a little bit sneaky on our algebra, as r squared minus 2r plus 1 plus 1 squared equals 0. All I did was I took the 2 and I broke it up into 1 plus 1. This then allows us to rewrite this as r minus 1 squared plus 1 squared equals 0, where this piece here is r minus 1 squared. Great. What's that do for us? Well, this will give us, if I take the square root of both sides, I'm going to have this r minus 1 squared plus 1 is 0, where r minus 1 squared is a negative 1. Uh-oh. This is going to give us r minus 1 equals plus or minus the square root of negative 1, which is I. And this gives us r is going to be equal to 1 plus or minus 1 times I. This is actually a double root. Okay, it's a double root because, oh yeah, it occurs twice. Yeah, we have a double root. Okay. Okay, so how do we treat this? Well, the first thing to realize here is that, thinking back to earlier times with Euler's function, we have alpha there, and we have beta there. So what we can do is we can use this idea here of c1 e to the rx plus c2x e to the rx for my double root. All right, so where's that take me? Well, what that does is that gives me the solution. Y is equal to c1, okay, e to the rx. It's actually c1 plus c2 e to the rx, and it's going to be times e to the x, and actually here, this should be a c2x. Got ahead of myself there, because we want c1 times e to the rx plus c2x times e to the rx. And what I did was I factored out the e to the rx to get that. Because in this case we're dealing with an imaginary situation, we're going to need to use Euler's formula here, where we bring in the sine and the cosine. So we have e to the x cosine of 1 times x, the 1 coming from the alpha, okay? Then we're going to have plus, we're going to do the same thing over again, C3 plus C4x times e to the 1x, because alpha is 1, and this time we wind up with sine of x. And remember, the beta is not the I value, but the beta is the coefficient in front of I. So that's why both your cosine and your sine, which should have beta times x, really just winds up being x. All right. Well, with those in mind, why don't you give a shot to the following? Pause the calculator, the computer. Try solving this. We have y to the fourth derivative plus 2y to the second derivative plus y equals 0. Develop your characteristic equation. Go ahead and factor that and see how that works out for you. Hopefully you actually did pause this and at least give it some thought, trying to figure out what direction you should go with this. First, the characteristic equation is going to be r to the fourth plus 2r squared plus 1 equals 0. Remember, r prime or y prime is going to give you your r. Okay, so we've got this, and now we need to factor this. Well, this will factor. This factors into an r squared plus 1 squared equals 0, which is going to give us r squared plus 1 equals 0, which then, if you solve for that, it's going to give us r is equal to plus or minus I. We're going to use the same idea of the general solution using repeated roots. And what we're going to wind up with this time is we're going to wind up with y is equal to c1 e to the I times x plus c2x e to the I times x plus c3 e to the negative I x plus c4 x e to the negative I x. And that's got that one worked out. Happened pretty fast. Okay, notice here that as we're looking at this, the value for alpha is 0, and the value for beta right there is 1. Okay, so that's how that one works out for you. To finish things off, let's do a last example here I want you to try by first pausing the video after you've got the problem copied down. Give this one a shot. This one's going to be a little more involved. We have the third derivative of y plus 12y squared, second derivative, plus 36 times the first derivative of y equals 0. And we have some initial conditions. Y of 0 is 0. Y prime of 0 is 1. And y double prime of 0 is a negative 7. By having these three initial conditions, remember we're ultimately going to wind up with a system of equations. Okay, we're going to have our general solution, and from that we're going to do our function where x is 0 and the y value is set equal to 0. The derivative of our function where x is set equal to 0, because the x value is 0 there, and the y value is 1. Then we're going to need to compute the second derivative, setting the x equal to 0 and y equal to negative 7. And that's going to give you a system of equations that you're going to need to solve by row reduction or the Gauss-Jordan method. Go ahead, pause, wrestle around with this, see how it goes for you. As you get stuck, go ahead and play through a little bit further in the video. And when you get unstuck, pause the video and keep going. Go get them. All right, let's have it this one more time. First thing I'm going to do is write this out as the characteristic equation. This is going to give me r cubed plus 12r squared plus 36r equals 0. Notice there is no y term, so there is no constant in our equation. We can factor out an r here. This is going to give us r times r squared plus 12r plus 36 equals 0. The good news here is this factors, and r times r plus 6 squared equals 0. This gives us a double root. Now remember, if we're in the double root scenario, we wind up needing to use things like e to the rx and x e to the rx. This could actually be a C1 and this could be a C2. Okay. Okay, but we also have this root of r equals 0. So first assigning the root r equals 0 in our solution, we get y is equal to C1 e to the root 1's value, 0 times x, plus C2 e to the value of the root. Now be careful here. The root here is going to be negative 6. This is going to be a negative 6x plus C3. Here's where the adjustment for the double root comes in. We have x e to the negative 6x. Okay, so we have that. We also have some information about the initial values here. That's going to have to disappear because I'm going to need to compute not only the function, okay, which I already have, but I'm going to need to compute the derivative and the second derivative, which the good news here is it's not that hard. If you take a look in this first equation at the top, we have C1 e to the 0 times x. That's really just C1. So when I compute its derivative, I'm going to have a negative 6 C2 e to the negative 6x. Then I'm going to have the derivative of this third term is a product rule. So it's going to be plus C3 e to the negative 6x minus 6c3 x e to the negative 6x. So when I computed this using the product rule, I first took the derivative of x, which gave me c3 e to the negative x. Then I took the derivative of the e to the negative 6x. Okay, so there's my first derivative. Can factor out the e to the negative 6x stuff. And what this gives me then, if I substitute in, let's see, what am I going to substitute in? Coming back up here to the top right-hand side. For the first derivative, the x value is 0 and the y value is 1. So I can rewrite this second equation as 1 is equal to, I'm going to substitute in a 0 for the x, which is going to give me a negative 6c2, and it's going to give me plus c3. This third term goes away because we have an x there, which is going to have a 0 in it. So that third term's gone. This gives me my second equation looking like that. The first equation, might as well come back and pick that up before we get too far down the road here. Notice for the second equation, or the first equation, our initial value information was y of 0 equals 0. So we're going to get 0 is equal to, now I'm going to plug in 0 for each of the x values here. I'm going to have C1 plus C2. Now when I plug in the x value here, this is all gone, okay? Because you have x times e to the negative 6x, but that x is a 0, so that's cleaned up. Okay, moving on to the second derivative. I need to compute the derivative of this first term, which is going to give us a 36c2 e to the negative 6x. Then we're going to have a minus 6c3 e to the negative 6x. Then for this one, we're going to have to use the product rule again. Okay, and when we use this product rule on this third one, we're going to wind up with, let's see, we're going to have a negative 6 c3 e to the negative 6x. Then we're going to have the derivative of e to the negative 6x plus 36 c3x e to the negative 6x. Okay, so there's that. All right, so what are we going to do from here? Well, we're going to come back up and we're going to check our information about the second derivative, which is in the upper rightmost corner. X value is 0, y value is negative 7. So we have a negative 7 equals. Now, when I plug in 0 into this first term, I'm going to wind up with 36 C2. When I plug in 0 into this second term, we're going to get negative, well, actually, hey, look at here. Look what we have. We have two of these. This is a negative 12 C3 e to the negative 6x. When I substitute 0 in for x there, I'm going to get minus 12 times C3. And then for this last one, when I substitute 0 in for x, that term goes away. Okay, so I have my three equations. And I'll put these three equations in this yellow box right there. Let's try that again. Three equations in that yellow box right there. So what I'm going to do now is to set up an augmented matrix. Okay. Remember, I'm going to do the matrix. I'm going to have my C1, C2, C3, then what's on the other side of the equation. So it's going to work out like that. And when I copy these down, notice this first equation all the way at the top is 1c1 plus 1c2. So we have 1 times c1, 1 times c2. There are no c3s equals 0. The second equation, now at the top, is going to be a minus 6c2 plus c3. So we have a minus 6c2 plus c3, and that equals 1. But notice there were no c1s. In the third of the equations, we have a 36c2 minus 12c3. So we have a 36c2 minus 12c3. And the right-hand side here is a negative 7. And once again, there were no c1s. Well, the good news here is in this matrix, the first column is already zeroed out. So it just doesn't get any nicer than that for you. I can rewrite this. I want to, in the second column, create a 1 here. So I'm going to multiply that second column by a negative 1/6. So I'm going to get a 0, a 1, a negative 1/6. And then on the right-hand side, we're going to get a negative 1/6. Okay, I'm going to now take this times a negative 1 and add it to the first row. The first row has a 1 here, plus a 0 gives a 1. I'm going to take this negative 1 times 1 gives me a 1 that's negative, plus the 1 over here that's positive, and that'll give us a 0, because 1 minus 1. Now, I'm going to take the negative 1 times the negative 1/6, which is a positive 6th. I want this location right here, which is this. Aha. So 0 plus a 6th is going to be a 1/6. And then when I take the negative 1 times the negative 6th, it's going to be a positive 1/6, plus the 0 is going to be a 1/6. Okay, so things are moving along pretty good. For the third row, I'm going to simplify this a little bit as far as the actual algebra involved. I'm going to go back to the first scenario, the first matrix, and I'm just going to multiply this by 6 and add it to the third row. And the reason is if I take this 6 times a negative 6, aha, that'll clear out my 36's. So I have a 0 plus 0 is 0. I'm going to have a minus 36 plus 36 is 0. Then I'm going to have a 6 minus 12 is a negative 6. Then I'm going to have a 6 times 1 is 6. Minus 7 is a negative 1. Okay, so that's got that all cleaned up. The next thing we need to do is I'm going to need to multiply this third row times a negative 1/6, or divide by negative 6. When I divide that third row by a negative 6, I'm going to get 0, 0, 1. Dividing by a negative 6 or multiplying by a negative 1/6 is going to give me a positive 1/6 over on the right-hand side. Now, I need to multiply this times a positive 1/6, add it to row 2. The 0 here plus the 0 in the second row is 0. The 0 here plus the 1 in the second row is 1. Now I'm going to have a 1/6 minus a 6 is 0. Lastly, I'm going to have a 1/6 times a 1/6, which is a 36th. Minus 6 over 36 gives a minus 5 over 36. Get to really brush up on your fractions here. In the first row, I need to zero out this positive a sixth. So I'm going to multiply by a negative 1/6, then add it to the first row. First, I have this 0 plus the 1 that's already in the first row will give me 1. Now I have this 0 plus a 0 that's already in the first row will give me a 0. Now I take the negative 1/6 times the 1, which is a negative 1/6, but I'm going to add it to the positive 1/6 that's circled in yellow, which will give a 0. So there's that. And the last thing we're going to do here is we're going to have a negative 1 over 36 plus, up here in the right-hand corner, 1/6. Well, that's 6 over 36 minus 1 over 36 gives a positive 5 over 36. Now that we've got this done, we can see that C1 has a value of 5 over 36. C2 has a value of negative 5 over 36. And C3 has a value of a positive 1 over 6. With that, we can now rewrite our general solution. Recall that our general solution looks something like C1 plus C2 e to the negative 6x plus C3 x e to the negative 6x. See if I can find it up here somewhere. Here it is. Okay, here was our general solution right there. Okay, there's where we started out. Now, we know the values for C1, C2, and C3. So all I need to do here is to substitute my value C1, 5 over 36. My value C2, well, it's going to be plus a minus 5 over 36 e to the negative 6x. Then for my C3, it's a positive 1/6 times x e to the negative 6x. And there you have it. That is the solution for that particular problem. I hope these help you some. Go get them on the homework, and I wish you the very best.